Okay, so we're going to do a whole unit on graphing rational functions, and you'll probably remember from Algebra 2 that rational functions can do all kinds of wonky things, and they can be really scary. Almost as scary as trying to make crepes without a non-stick pan. But if you just do the steps, get into the rhythm of it, you can do this just as easily as if you're graphing a parent function that has more predictability. So, let's talk about what it is to be a rational function first. Remember, these are of the form p of x over q of x, where we have to be really careful that q of x can't equal 0. And the really cool thing about that when it comes to graphing is whenever you find one of these, it's an asymptote or a hole in the graph. So that's one of the things that we'll use to graph a rational function. It gives us a lot of information. So let's look at the one we have here and see. First, let's find the things we're used to finding. Let's find the y-intercept. We're going to do exactly the same thing that we would do with any other graph. The y-intercept is wherever x equals 0. So the f of 0 equals 3 times 0 squared minus 3 over 0 squared minus 9, but that's just 0. Negative 3 over negative 9 is positive 1/3. So I now know that the y-intercept is at 0, 1/3. Okay. That's a lot of information. Now let's look for the x-intercept. So the x-intercepts are wherever y equals 0. But notice, I can never let y equal 0 by letting the denominator equal 0. So those values are already eliminated. All I have to do is find out where does the numerator equal 0. The numerator equals 0 wherever the f of x or the f of x, equals 3x squared minus 3. And if I let just the numerator equal 0, I will find the x-intercepts. So that would be 3x squared equals 3, x squared equals 1, 3 divided by 3, and so x equals plus or minus the square root of 1, which equals plus or minus 1. So now I know where the two x-intercepts are. They're at 1, 0, and at negative 1, 0. So the next thing I want to find is the vertical asymptotes. And we already alluded to vertical asymptotes are wherever the denominator equals 0. So I'm going to let the f of, and I probably shouldn't choose f, I should probably choose another value. So let's let the h of x be the, let's let the p of x be the numerator, because that's what we used up here, right? So the p of x is the numerator, so the q of x is the denominator, and we know that it can't equal 0. So when the q of x is x squared minus 9, not allowed to be 0, well, that's at x equals plus or minus the square root of 9, which is at plus or minus 3. So now I have 3 important pieces of information and 5 important pieces of data, specific data points. So at 3, 0, and at negative 3, 0, I know there's an asymptote. So let's go ahead and put that in. So I'm going to put, let's see, negative 3, 1, 2, 3. I'm just going to dot that in. Doesn't have to be dotted, but, and this is the line x equals negative 3, and I can dot in positive 3. So x equals 3. I can also place my intercepts. I have an intercept at x equals 1, and I have an intercept at x equals negative 1. and I have a y-intercept at x equals 1/3. So I actually have a huge amount of information now. I know exactly what's happening here in this middle spot. And I know it because I know that this is true. I know I have an intersection or a root at -1 and +1, which means I have a y-intercept at 1/3, which means that this part of the graph has to be happening. And we also know that asymptotes are defined as lines that our curve will get closer and closer and closer to without going over. So I have 1/3 of my graph in place, hardly doing any work at all. So to find the rest of it, well, let's think about what could be happening. It is possible that I have something happening like this, right? So it goes closer and closer to the asymptote here, but it would go up off to infinity over here. But I know that's not true. Already I know that's not possible because it has a solution right here. It has a 0 here. If the graph does this, there would be a 0 here. And the calculations to find my zeros, I didn't get any more zeros. So that is not possible. Another possibility is that it comes up like this and just scoots off toward infinity, getting closer and closer to the x-axis. That's certainly possible. It doesn't require a 0. It's not eliminated by having a y-intercept. It respects the vertical asymptote. It could do the same thing on the other side. Or it could do this, approaching 0, or it could be doing this. But I know it's not going to do anything that looks like this because it wouldn't pass the vertical line test. So in the middle of the two asymptotes, I'm finished. I know I'm finished because it's totally exhausted all possibilities for a function. But it is possible that I have just identified the 0, the x-axis as an asymptote, but there may actually be another asymptote in this graph. There may be something like, maybe this is an asymptote and the graph is going to be like this, right? It's not going to go below this line. So I'm going to have to do a little bit more work to find out. And the first bit of work I want to do is find if there's a horizontal asymptote. Because finding the vertical asymptotes was so helpful, let's find the horizontal asymptote. And remember, to find horizontal asymptotes, there's a rule that goes in place, right? A little bit of calculation, but mostly just a rule. Not like the vertical asymptote where you just set the denominator equal to 0. The horizontal asymptote has more to do with the degree of the polynomial than it does, the rational number, than it does particularly the numerator or the denominator. So let's write that rule down and review. So we want to look at the degree of the numerator over the degree of the denominator. We want to make a comparison of these two. And when we compare them, actually I should make this the other direction. When we compare them, if the degree of the numerator equals the degree of the denominator, then there is a horizontal asymptote at the leading coefficient of the numerator divided by the leading coefficient of the denominator. And we can see that this is our case here. It's a second degree and a second degree. The leading coefficient over the leading coefficient is 3/1. So in this case, for our function right now, that equals 3/1, which equals 3. So I do know, in fact, that there is a horizontal asymptote at y equals 3. So 1, 2, 3, right here. And I can dot that in, and I can label it y equals 3. So I sort of already know what's happening with my function, because if y equals 3 is an asymptote, this is not possible because I would have gotten that root out of my calculations. So I know that my graph has to be going like this on both sides. Not that I'm not going to confirm that, but I already know that this is the shape of this graph. But let's go back and finish up our rule about horizontal asymptotes. If the degree of the numerator is less than, excuse me, greater than the degree of the denominator. Oh, let's do the other direction first. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the origin y equals 0. Excuse me, the line, the x-axis at y equals 0. If the degree of the numerator is greater than the degree of the denominator, you're going to look for a diagonal asymptote with synthetic division or long division. And we'll do an example like that in a minute. Okay, so what's the other bits of information I could use here? Well, I could test a point. So suppose I'm not really sure. I mean, I guess I could think that maybe it does something like has a hole here. It's possible for a graph to have a hole, to come up and go like this, and I want to be sure. I have my best tool, my oldest tool, my best friend from a long, long time ago. I'm just going to plug in a point. I'm going to point check. So I'm just going to put in the f of, well, if this is 3, let's put in the f of 4. Equals 3 times 4 squared, so that's 16 times 3 is 30, 48, minus 3 over 16 take away 9 is 7. And at this point, all I really care about is knowing just by inspection that this is a positive and a positive, which means my value is positive. Oh, actually, I guess I do care that it's more than. I care that it's positive, and clearly 48 take away 3 is 45/7 is a number greater than 3. And so I know that it has to be above, my graph has to exist above my horizontal asymptote. And by doing a similar calculation on the other side, on the negative side, but I can do it in my head, and you can do it in your head too, because I got the value I got here by plugging a positive 4 into a function where all of the x's are squared. So if I plug in a negative 4, they're going to become positive. I'm going to get exactly the same result. So this would be that graph. Let's do one more, maybe 2 more, because I think these are a load of fun. So let's look at one that has a diagonal asymptote. There's one in your textbook I think I'm going to use. So if I want to graph y equals 2x cubed over x squared plus x minus 12. So I want to graph this. All right, I'm going to do exactly what I did before. I'm going to look first for my y-sept. And that's wherever x equals 0, just like always. And I don't really have to plug it all in because the numerator is going to be 0, and I just have to be sure that I'm safe, that I'm not choosing a denominator value or a excluded value. So a 0, 0 would leave negative 12 in the denominator, perfectly reasonable. Numerator equals 0, so my y-intercept equals 0, or let's write it as a point, is at x equals 0, y equals 0. So at the origin I have a y-intercept, which means I kind of know at least one of my x-intercepts, right? One of my solutions. So this is at p of x equals 0. So my x-intercepts are wherever the numerator equals 0. And so I can see that the p of x equals 2x cubed equals 0 at x equals 0. So it looks like when I found the y-intercept, I actually found the only solution as well. So this would be at 0, 0 as well. So now I want to find some vertical asymptotes, and the vertical asymptotes are at q of x equals 0. It's an undefined denominator. So q of x is x squared plus x minus 12 equals 0. So x plus 4 times x minus 3 equals 0. So I'm looking at x equals negative 4 and x equals positive 3. So my asymptotes are the lines x equals negative 4 and x equals 3. I think I wrote these as a point before. That was a mistake. I apologize. Our asymptotes are not at points, they're at lines. They intersect at a point with the x-axis, but they're actually lines. So now I want to find my horizontal asymptote. So horizontal asymptotes, remember there's a rule, so I just ask, and in this case, the degree of my numerator is greater than the degree of my denominator. So I want to do division to find the vertical asymptote. So I think I'm going to come down here to do it so I have lots of room, because we haven't done this before. Even in Algebra 2, I don't think we did this. So if our denominator, or if our function, I'm going to write it out again, is 2x cubed over x squared plus x minus 12. So I want to do division with this. I wish I could do synthetic division, but I can't because I have a denominator that isn't linear. So I have to do long division, polynomial long division. So 2x cubed plus 0x squared plus 0x plus 0 is my numerator, and I'm going to divide it by x squared plus x minus 12. So 2x squared times 2x would give me 2x cubed. Now I distribute. 2x times x squared is 2x cubed. 2x times x is 2x squared, and then 2x times negative 12 is negative 24x. I want to subtract, which means change all the signs inside and turn it into addition. So now I can cancel. These cancel automatically. I set it up that way. 0 minus 2 is negative 2x squared, and then 0 plus 24x is plus 24x. I'm going to bring down the 0, and then I just repeat the process. X squared times negative 2 equals 2x squared. Excuse me, negative 2x squared. Negative 2 times x is negative 2x. Negative 2 times negative 12 is a negative 24. Subtract, which means change all the signs and turn it into addition. First cancels. First terms cancel by design. 24x plus 2x is 26x, and 0 plus 24 is plus 24. I think I made a mistake here. Negative 2 times negative 12 is a positive 24. When I change the sign, I get a negative 24, so this should be minus. It's not going to really matter in this situation, but it's always a good idea to be careful. So I have 2x minus 2 plus 26x minus 24. That's still, because this is a remainder, right? That still needs to be divided by the x squared plus x minus 12. Now in this case, we don't care all that much about the remainder and the third term here, the rational term, but we care that this first part of it is a line, and this line has a slope of 2 and a y-intercept of negative 2, which is our diagonal asymptote. I always thought that was just cooler than cool. So 2x minus 2, that line is our diagonal asymptote. Now I know it's under the horizontal asymptote heading, but that's just because it's part of that rule where we look for the horizontal or diagonal asymptotes. So when we have a numerator that is greater than a denominator, then we look to see if there's a diagonal asymptote. I should say by exactly, if the numerator is greater than the denominator by exactly 1 degree. then we're going to use synthetic or polynomial long division to find the line that represents the diagonal asymptote. All right, so let's put together everything we have and get this over with. We have a y-intercept. Oh, let's look at our asymptotes first. We have vertical asymptotes at -4 and 3. So at x equals 3 and at x equals 1, 2, 3, 4, -4. So at x equals -4 and x equals 3. And we have a diagonal asymptote at the line that intersects at -2 and has a slope of 2. So rise 2, run 1. So this is our diagonal asymptote. So just like before, we have, if I make this show up a little bit better to remind us, we have 6 regions on the graph to try to determine what happens to this graph. Now, I should tell you, diagonal asymptotes are not as picky about being crossed as other asymptotes. So when you're looking for the behavior where the graph cannot cross it, diagonal asymptotes are a little bit less picky. They're a lot less picky. And I don't really know why. If somebody can explain that, that would be really fabulous. But I can never cross a horizontal asymptote. I either have a hole or a horizontal asymptote. So let's look. I have to decide whether, here are my choices. Let me sketch them in a light color. This could go, well, we know it doesn't do this, right? Because if it did, I would have found that root. And it could do something that goes like this, but we know it doesn't do that either. Because if it did, x would have been the x-axis would have been an asymptote, and the x-axis is certainly not an asymptote. So I pretty much know that the graph lives here. And I'm going to confirm that by plotting a point. I also, by the same logic on the other side, I know that the graph lives here, in this area. Because if it lived like this, I would have gotten a root. And if it lived like this, I would have known that I would have gotten an asymptote. So I know that the graph lives here and here. Now this part, I know that I have an intercept at the origin. Okay, so that works. I have a y and an x-intercept at the origin. And that's all I know. So because the only thing here, I might want to say, oh, it must do this, or maybe even like this. Well, I can't do that because I didn't get another root, right? I would have gotten a root if it did that. So it's possible that it does this, but I will tell you, we're not so concerned about crossing diagonal asymptotes. So the graph could actually go like this. And if I plot points, and I'm not going to do it to save time on the video because you know how to plot points, but that's exactly what happens. This graph lives here and here, and then it comes down like this and goes across to this side. Okay, I know the video's gotten long. I apologize for that. I have one more thing that you need to talk about, and that is, remember when I talked about there being a hole? Sometimes there's a hole rather than an asymptote, and I'm going to show you when that happens. So suppose I'm graphing y equals, let's see, x squared minus 9 over x plus 3. First thing I would notice is that Q of x requires that there be an asymptote at x plus 3 equals 0. So this would be x equals minus 3. So we're never allowed to choose -3. That's a restriction on the domain, so you're going to get an asymptote. However, in this case, we don't get an asymptote there. What we get is a hole in the graph. And so the reason for that is if I factor the numerator and I get x plus 3 times x minus 3 over x plus 3, when I cancel, I actually have turned my function into y equals x minus 3, which is just a line. In fact, this function is going to graph a line. If you graph this function in a graphing calculator or go to Desmos, this whole function is going to give you a line, and the line is going to be x minus 3. So it's going to be like that. But because the function is defined by this rational number that has a denominator that can't equal 0, this graph is really going to have, at x equals minus 3, this graph is really going to have a hole in it, and then it's going to continue on at x equals negative 3. So if you can factor out and get rid of the problem in the denominator, then what you really end up with is a graph with a hole in it, not an asymptote. But that's the only time. And if you look at the functions that we've done up here, there was no factoring that would let me get rid of the problem in the denominator. And up here, there was no factoring, even though it sort of looked like it for a minute, there was no factoring here that was going to let me get rid of the problem in the denominator.